Welcome back, everybody. Today we're going to talk about our first lesson in our exponent and logarithms chapter. Today we're talking about growth and decay functions. Exponential growth is when our graph is increasing from the left to the right. So what's the difference between an exponential function and a regular function? Well, the difference is that the variable is the exponent rather than the base. So rather than being 2x or x squared, where x is our base, now we're talking about 2 to the x power or 3 to the 3x power. So our variable is in our exponent. Exponential growth increases slowly at first. You can see over here on the left side of our graph, it's very slow. And then all of a sudden, it drastically increases as we're going to the right and time continues. A couple of basic things about our graph. 0, 1 is what we call our go-to point. That is always going to be in our parent functions. And then we have a horizontal asymptote here at y is equal to 0. Now remember, an asymptote is a line that our graph will approach, but will never touch or cross. Where does the 0, 1 come from? Well, remember, if I have an equation like 3 to the x, and I plug in that 0, anything to the 0 power is 1. So it doesn't matter what our base is. Anything to that 0 power is going to be 1, and that's why 0, 1 is going to be our go-to point for our basic parent function. Here is our equation for that graph that we just saw. B to the x power, and in this case for growth, B has to be, our base has to be greater than 1. So it can be 1.2, 1.1, 1.009, it can be 3, put my exponents up here, it can be 4, it can be 17. As long as it's greater than 1, then it's a growth, exponential growth graph. So again, our go-to point always passes through at 0, 1. Horizontal asymptote at y equals 0. Exponential decay. So decay starts off with a very rapid decrease, and then it slows down. Our base is between 0 and 1. So basically, the base is a fraction, but be careful, because if I have y is equal to the 3/2 x power, 3/2 is more than 1. So you still have to pay attention to the base to make sure that your fraction is less than 1. Still has that same go-to point at 0, 1, and still has that asymptote at y equals 0. So for graphing, we're going to pick at least 3 values for x, plug them in to find y, and then graph your points. Make sure that you also have your asymptote. And for all of these graphs, our asymptote will be at y equals 0 because these are parent functions. So if I pick -2, 0, and 2, and plug them in, we have 2 to the -2nd power is 1/4. Remember, negative exponents never make negative answers. They just take the base and flip it under 1. Or if you put that in your calculator, you would have gotten 0.25. 2 to the 0 power is 1. Anything to the 0 power is 1. And then 2 squared is 4. make my graph. So we have -2/4, 0, 1, and 2, 4. And here is my growth graph. And I know it's growth because 2 is more than 1. Oh, and my asymptote. Always make sure that we label our asymptote even if it's an axis. All right, so I'm again going to pick -2, 0, and 2. 3 to the -2nd power is 1/9. 3 to the 0 power is 1. And 3 squared is 9. And we have 9 there. So I'll plot my points. -2, 1/9 is going to be super close here to our asymptote, 0, 1, and 2, 9. And there's our graph. It's again exponential growth because our base is greater than 1. And our asymptote at y equals 0. All right, exponential decay functions. Again, we remember that these are decay because 1/2 is a fraction that's between 0 and 1, and 1/3 is a fraction that's between 0 and 1. I'm again going to pick the -2, 0, and 2 for each of these. So 1/2 to the -2nd power is 4. 1/2 to the 0 power is 1 because again, anything to the 0 power is 1. And then 1/2 to the 2nd power is 1/4. You'll notice it's exactly opposite of the last slide with the last example of growth for y equals 2 to the x. So that the same thing's going to happen over here on this side. 1/3 to the -2nd power is 9. 1/3 to the 0 power is 1. And 1/3 squared is 1/9. I make a sketch. And I'm going to change colors here. So we have -2, 4, 0, 1, and 2, 1/4. There's my decay function. And my asymptote is still at y equals 0. And then over here for my 1/3, we have -2 to the 9th, 0, 1, and 2, 1/9. With our asymptote at y equals 0. Solving real-world problems. This is where we are evaluating. Remember, evaluate means we're plugging something in. And so we have an equation for the value of a car because cars depreciate, so it only keeps about 85% of its value, or it depreciates by 15%. T is the number of years since the car was new. So this is exponential decay, and again, the base is always going to be the one that's exactly to the left of the exponent. 0.85 is our base, it's less than 1. So it's decay. It is decreasing by 15% because 100 minus 85 is 15. Because remember, 100% of the value means it keeps all of it, and we're at 0.85. So estimate when the value of the car will be $8,000. And so here's what we'll do. We have 25 times 0.85. And then where this T is, we're just going to keep trying some numbers. So anything you want, really, to get to as close to 8,000 as we can. So I'm going to plug in maybe 5 years and then 6 years. I'm getting closer, but it's not quite close enough. I'm going to try 7 years. And at 7 years, it's actually worth $8,014. And that's going to be the closest I can get to 8,000. So we'll estimate about 7 years. Here's another problem with depreciation of cars, because we all know that as soon as you drive off the lot, you lose value in your car. So is it growth or decay? Again, locate the exponent, and the number immediately to the left of it is the base. We have 0.92. 92 hundredths, or 92%, is our base, and 0.92 is definitely in between 0 and 1. So we're again at a decay problem. 100 minus 92 is 8%, so it's decreasing by 8%. The last part it's asking us to do is to estimate when the value of the car will be $9,600. Now it took 7 years for the last car to get to our estimate, and that was at 15%. This is only 8%, which means it's going to take a lot longer. So in your calculator, we will do 31, and then we'll have 0.92 and then we're filling in this value up here with what you think it'll be. So I'd say maybe try 11 or 12 to start with. And keep going and keep going, keep going until you get as close to 9,600 as you can. And so when I do this math, I get to be about 14 years. All right, our growth model. This is a very basic exponential growth problem. It's calculating simple interest. If you were to take a loan or put in money to accrue interest and invest. So our initial amount is the A. The percent that we're increasing is the R. It's written as a decimal. So let's go back and remember that anytime we want to change a percent into a decimal, let's say it's 18%, and the decimal technically is right here, we always move the decimal left 2 places to get the decimal part that we would put in for R. So left 2 places. And then T is the number of years that you're going to leave it invested for. So let's take a look at this example. So the initial amount that we are investing is $25,000. Our percent increase, remember you take that 0.13 and move the decimal the opposite direction to get the percent, and that's 13%. So our initial investment is $25,000. It's gaining 13% annually, and 5 is the number of years that we're going to leave it in for. The next example is asking us to start with writing the growth model. So write the growth model. We have y is equal to our initial amount in 2000 was 6.09 billion. So we're going to put 6.09 here and note that our y is going to be in billions. Parentheses 1 plus our growth rate is 1.18%. Now remember, we have to move it over twice. We have to fill that empty hole there, so that's a 0.0118, and then T amount of years. So that's our equation. Now let's estimate the population in 2005. So 2000 to 2005 is 5 years. That means that our T is going to be 5. So we have 6.09 times 1 plus 0.0118 to the 5th power. Type that into our calculator and we get roughly about 6.46, and remember that's in billions. So 6.46 billion would be the world population in 2005 according to this growth model. Decay. Here's our equation for decay. You can tell the only difference between the growth and the decay is the subtraction. And that's kind of the clue that we're going down rather than up. So A is still your initial amount. R is the percent decrease written as a decimal, again, moving the decimal twice. And T is still the number of years. So in our first example, our initial amount is $15,500. Our decrease, our rate of decrease is 17%. Remember, you move the decimal twice the opposite direction to get back to the percent. And we have a time frame of 7 years. So that would find the amount that some purchase we made for $15,500 would be worth at after 7 years when we decrease it 17% per year. So for our second example, writing our formula, we have 35,357 as our purchase amount times 1 minus 13%, which is going to be 0.13 to the T power. So that's the equation. Remember, it asks us technically for 2 things. It asks us for the equation, and then it asks us to find the value after 6 years. So in this case, we'll change our T to 6, and our BMW 3 Series would be worth roughly about $15,331.72. So you lost $20,000 of value over 6 years. All right, this is where we're going to stop for today. We're going to talk about compound interest in class tomorrow. Have a good night.